A significant upheaval in the natural order is unfolding across the vast, deep indigo of the Atlantic Ocean, a disturbance so profound that its implications are only beginning to be understood by the scientific community. The sea, which has swallowed armadas and ground continents to sand, is being violently displaced by an object of almost incomprehensible scale and power. It is a man-made island of steel, wire, and nuclear fire, measuring 1,092 feet from bow to stern and weighing a staggering 100,000 tons. To the naked eye, from a few miles away, it moves with the deceptive, slow-motion grace typical of massive ships. But close the distance, and the illusion shatters. The ocean is roaring. A towering rooster tail of churning white water kicks up from the stern, and a massive bow wave crests and shatters against the gray steel hull. The ship is moving in excess of 30 knots, well over 35 miles per hour. For a vessel of this size, that speed is not just a feat of engineering, it is a defiance of physics. But straight line speed is only the preamble. Suddenly, the massive flat-topped silhouette begins to lean. The horizon tilts. One side of the 4.5-acre flight deck dips precariously close to the rushing ocean, while the other side rises toward the sky. The wake, previously a straight churning highway of foam, bends into a violent, frothing arc. A 100,000-ton nuclear-powered city is drifting. This is the USS John F. Kennedy, CVN-79, the United States Navy's newest and most advanced supercarrier. At a price tag of roughly $13 billion, she is the second vessel of the revolutionary Gerald R. Ford class. And what she is executing right now, the high-speed turn, is one of the most brutal, awe-inspiring, and critical crucibles in the life of any warship. It is a spectacle that combines the raw, visceral thrill of a race car sliding through a hairpin curve with the apocalyptic energy of a controlled nuclear reaction. To understand the magnitude of this maneuver, one must first look beneath the armored skin of the Kennedy. The era of oil-burning boilers belching black smoke is long gone. The Kennedy is propelled by two A-1B nuclear reactors. These marvels of modern atomic engineering are designed to run for the ship's entire 50-year lifespan without ever needing to be refueled. They generate an amount of thermal energy that borders on the mythical, converting purified water into high-pressure, superheated steam. This steam is directed into massive turbines, which spin at phenomenal speeds. That rotational energy is transferred down four immense steel shafts, each stretching the length of a football field through the lower decks of the ship. At the end of these shafts, extending into the cold ocean water, sit four solid bronze propellers. Each of these screws weighs approximately 30 tons and spans 21 feet in diameter. When the captain orders flank speed, the reactors surge, the steam howls through the piping, and those four bronze leviathans bite into the water. They don't just push the ship forward, they carve a canyon through the sea. The power output is so immense that it is classified, but it is enough to generate over 250% more electrical capacity than the legacy Nimitz-class carriers. But accelerating 100,000 tons in a straight line is merely an exercise in thrust. Turning it at high speed is an exercise in structural agony. When the order for a high-speed turn is given on the bridge, the helmsman does not wrestle with a massive wooden ship's wheel. In the digital age of the Ford class, the helm is remarkably compact, controlled by advanced software and precise electronic inputs. The helmsman turns the wheel hard over, commanding maximum rudder angle. Deep beneath the stern, two massive rudders, each the size of a small house, pivot into the roaring high-velocity slipstream created by the four spinning propellers. The water slams into the flat surfaces of the rudders. The hydrodynamic force generated in that split second is almost unimaginable. Millions of pounds of pressure are suddenly applied to the stern of the aircraft carrier, attempting to kick the back of the ship outward. For a brief, suspended moment, the Kennedy seems to resist. Sir Isaac Newton's first law of motion dictates that an object of this mass desperately wants to keep moving in a straight line. The ship shudders. A deep, resonant groan echoes through the steel bulkheads, traveling up from the keel, through the hangar bay, and up to the flight deck. It is the sound of 1 billion pieces of metal fighting against the ocean. And then the ocean yields. The bow begins to sweep across the horizon. As the turn tightens, the ship experiences a dramatic heel or list. Centrifugal force pushes the massive superstructure outward, while the hull digs into the water. On the flight deck, the angle is startling. Standing on the port side during a hard starboard turn, a sailor would look down and see the churning, violent sea rushing past just a few dozen feet below the deck edge, far closer than it was moments ago. On the starboard side, the deck slopes sharply upward, presenting the non-skid surface to the sky. If there were aircraft on the deck, sleek F-35C Lightning IIs or FA-18 Super Hornets, they would be heavily chained down to the specialized pad eyes welded into the steel. Anything not chained down, a toolbox, a tractor, a careless sailor, would be sent skidding across the abrasive deck toward the precipice. But during these specific builders and acceptance trials, the deck is kept deliberately clear of aviation assets. The focus is entirely on the ship itself. Down in the bowels of the Kennedy, the experience of the high-speed turn is intensely sensory, though entirely different from the visual spectacle above. In the engineering spaces and reactor control rooms, there are no windows to the outside world. The crew relies entirely on a complex matrix of digital displays, dials, and sensors. When the rudders bite and the ship leans, the deck beneath their boots tilts dramatically. Sailors instinctively widen their stances, grabbing on to permanent handholds or leaning against bulkheads to maintain their balance. Coffee cups left unattended slide off desks and shatter on the steel decks. But the real drama is playing out on the monitors. As the ship carves into the turn, the resistance of the water spikes massively. The propellers are no longer just pushing water backward, they are fighting the lateral movement of the hull. The torque on the 4 massive propeller shafts skyrockets. The engineers watch the dials intensely. The automated systems of the A-1B reactors sense the sudden massive demand for power to maintain the RPMs of the shafts against this new crushing resistance. The reactors automatically step up, providing more steam, fighting to keep the 100,000-ton beast from bleeding off its speed. This is the true purpose of the high-speed turn. It is not a publicity stunt, nor is it a joyride for the Admiral. It is a vital, non-negotiable component of the Navy's rigorous sea trials and the Board of Inspection and Survey, INSURV, evaluation. Before the Navy accepts a $13 billion warship and puts the lives of 4,500 American sailors aboard, they must know, beyond a shadow of a doubt, that the ship will not break when it is pushed to its absolute limits. The high-speed turn is a stress test of the highest order. The engineers are monitoring the temperature and vibration of the massive bearings that hold the spinning propeller shafts. If there is a microscopic misalignment in the shaft or a flaw in the lubrication system, the immense torque of the high-speed turn will expose it, causing the bearings to overheat or fail. They are monitoring the structural integrity of the hull itself. Does the steel flex too much? Do the welds hold? Does the piping system that carries high-pressure steam, chilled water, and aviation fuel rupture under the twisting forces applied to the ship's skeleton? They are also testing the steering gear itself. The hydraulic rams that pivot those massive rudders must push against millions of pounds of water pressure. If a hydraulic seal is going to blow or a pump is going to fail, the Navy wants it to happen now in the controlled environment of a trial, with shipyard engineers on board, not in the dead of night in a contested zone in the South China Sea. The John F. Kennedy carries an incredibly heavy legacy. She is the second aircraft carrier to bear the name. Her predecessor, CVN-65, the legendary Big E, or the original USS Enterprise, was the world's first nuclear-powered aircraft carrier. But before that, there was the conventionally powered USS John F. Kennedy, CV-67, a workhorse of the Cold War and the Gulf War. The name evokes a president who famously commanded a PT boat in the Pacific, a man intimately familiar with the unforgiving nature of naval combat. CVN-79 was built to honor that legacy, but also to transcend it. She benefits immensely from the pain and lessons learned by the first ship of her class, the USS Gerald R. Ford, CVN-78. The Ford was a clean-sheet design packed with revolutionary technologies that replaced reliable, century-old steam systems with digital electromagnetic counterparts. The transition was rocky. The electromagnetic aircraft launch system, emails, and the advanced arresting gear, AAG, suffered highly publicized teething issues. But the Kennedy was built with the advantage of hindsight. The shipbuilders at Newport News Shipbuilding refined the construction process. They built larger modules of the ship on land, outfitting them with piping and wiring before lifting them into the dry dock with massive cranes, a process that saved millions of man-hours. The software that controls emails and AAG has been debugged and matured. The Kennedy is not just a copy of the Ford, she is the refined, optimized realization of the class. Yet for all her digital brilliance and futuristic weaponry, she is still a ship on the ocean, subject to the same tactical realities that governed the aircraft carriers of World War II. And that is why the high-speed turn is not just an engineering test, it is a vital combat maneuver. Why would a 100,000-ton floating city ever need to drift like a sports car? The first reason is survival. In the modern era of naval warfare, the aircraft carrier is the ultimate prize for any adversary. They are hunted by ultra-quiet diesel-electric and nuclear-attack submarines. They are targeted by long-range, sea-skimming cruise missiles and hypersonic anti-ship ballistic missiles that fall from the edge of the space. If the Combat Information Center in the belly of the Kennedy detects an incoming torpedo, a high-speed acoustic nightmare tracking toward their propellers, the ship cannot simply absorb the blow. The captain will order a hard turn at flank speed. The goal is to present a smaller profile to the incoming weapon, or to outmaneuver the torpedo's acoustic seeker, throwing the massive ship into a violent evasive arc while deploying acoustic countermeasures and decoys into the water. A sluggish carrier is a sunken carrier. The agility displayed in these trials is the difference between life and death. The second reason is the unforgiving nature of naval aviation. Aircraft carriers do not operate in a vacuum, they are tethered to the wind. To launch a fully loaded fighter jet, the carrier must turn its bow directly into the wind, generating wind over deck, or WOD. This natural headwind, combined with the speed of the ship and the thrust of the electromagnetic catapults, creates the lift necessary to get a 60,000-pound fighter airborne. The same applies to landing. A pilot returning from a stressful combat mission, attempting to catch a wire on a pitching deck at night, needs the wind perfectly aligned down the angle of the landing area. But the wind is fickle. In a combat scenario, an aircraft carrier might be steaming in one direction to evade an enemy patrol, but suddenly receive word that a flight of F-35s is returning bingo, critically low on fuel. If the wind is coming from the opposite direction, the massive carrier must turn around, and it must do so immediately. There is no time for a slow, graceful 5-mile wide arc. The captain will order a high-speed turn, whipping the 1,092-foot behemoth around 180 degrees to catch the wind and save the pilots before their engines flame out. The sheer violence of the maneuver is the price paid for the safety of the air wing. As the Kennedy completes her trial maneuver, the helmsman returns the wheel to the amidships position. The massive rudders pivot back to neutral. The ship groans once more as the lateral forces dissipate. Gravity seems to right itself as the flight deck levels out, settling back parallel to the horizon. Behind the ship, the ocean tells the story of what just happened. A massive, perfect U-shape of bright white churning foam scars the deep blue surface of the Atlantic, miles wide and slowly beginning to fade. It looks as if a giant has dragged a giant chalk line across the sea. Down in the engineering spaces, the tension breaks. The dials stabilize. The reactors purr with infinite quiet power. The bearings hold. The seals remain intact. The hull did not buckle. The engineers and naval inspectors nod in quiet satisfaction, making notes on digital tablets. The ship has passed the crucible. The USS John F. Kennedy is more than just an assembly of steel and wire. She is a $13 billion statement of national will. She is designed to project power, deter aggression, and, if necessary, wage war with a level of technological supremacy that borders on science fiction. But beneath the advanced radars, the stealth fighters, and the electromagnetic catapults, she remains a vessel that must conquer the ocean before she can conquer the enemy. The high-speed turn, the violent, spectacular 100,000-ton drift is the ultimate proof of that conquest. It is the moment the machine proves it is worthy of the sailors who will call it home, worthy of the oceans it will patrol, and worthy of the legendary name it carries on its stern. As the Kennedy steams forward, leaving her massive, curved wake behind, she is no longer just a shipyard project. She is a warship, fully awakened and ready to dominate the next half-century of maritime history.
Enjoyed the episode? Like and subscribe to Military Forces. For more in-depth content, your support helps us create more.